In the previous class, we looked at a theorem about consecutive pairs of quadratic residues modulo p. It turns out that we can prove a similar result regarding consecutive triples of quadratic residues. While this proof is admittedly even more technical and more difficult than the ones from the previous section, there is a surprising corollary of the proof that we will need moving forward. Because of the length of the proof, it will be done in two sections. Definition. Let nu of p denote the number of consecutive triples of quadratic residues in the interval 1 to p minus 1. Theorem. If p is an odd prime, then nu of p is equal to p over 8 plus an error term, where the error is less than 1/4 squared of p plus 2. Unlike the statement for pairs of consecutive residues, we do not have an exact formula, but we do have an estimate on the size of the error. We will start off in a manner similar to the proof in the previous section. We first define c sub p of n as the function that counts the consecutive triples of quadratic residues. This gives us a formula for nu of p. Just as before, we can write an explicit equation for c sub p of n using Legendre symbols. We can plug this into the equation for nu of p and expand the product to get a long algebraic expression to work with. The first 7 of these sums are a type that we saw in the previous section. We will fill out the sums so that they are sums over a complete set of residues and then use our previous results to simplify it. Here are all the calculations. We won't be talking through them individually. We will move the p over 8 term to the left side and define the remaining quantity to be the error term. We will bound this above by maximizing all of the individually bracketed terms from the middle part with all the Legendre symbols. We will also round up the constant term because it's easier and doesn't have a significant impact on the end result. From here, we can see that the remaining challenge is to evaluate the sum of the products of consecutive Legendre symbols. Specifically, we must prove this inequality. In the next video, we will do that and finish the proof.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.